Right, we'll start with the topic on transmission impairment, right? This is a continuation from our previous lecture, okay? Week 2 and 3. So transmission impairment is a signals travel through transmission medium which are not perfect. So the imperfection causes signal impairment, and this means that the signal at the beginning of the medium is not the same as the signal at the end of the medium. So what is sent is not what is received. And the three causes of impairment are attenuation, distortion, and noise. So basically what it is trying to say that whenever, whichever type of equipment or transmission channel that you are using, there are chances of signal not being correctly transferred from the starting point to the end point. Okay? The signal can somehow change its form. Okay? So there are three ways or three causes rather, okay, of signal impairments, and that is attenuation, distortion, and noise. Okay? So three causes there of impairment. So starting with the attenuation, the first one here says if you see the original signal, right, and while the signal is being traveling through the transmission medium, at some point, right, somewhere the signal gets or rather changes its form. Right? If you look at that example there, attenuated, and then with the use of an amplifier, then the signal can be corrected. So there are chances or there are situations where attenuation can happen, and if there is attenuation, then you can correct the signal using an amplifier. An example of an amplifier is a repeater or a switch. Okay? You can place these two devices on your network, and those two devices can actually boost or repair the signal which has been corrupted and then resend it to the next to the further device. Okay. The example here says suppose a signal travels through a transmission medium and its power is reduced to 1/2. This means that P2 is half of P1. In this case, the attenuation, that is loss of power, can be calculated as, actually the formula, okay, to calculate attenuation is given here. That is 10 log 10 with the base 10, okay, and P2 over P1. P2 basically means the 0.2, right? And P1 is, of course, the initial of the source point. Right? Right. Now you can see 10, base 10, 2 over. So in this example here, it says 10 log 10. So in this case, it says P2 is half of P1, therefore 0.5 P1 divided by P1, and it gives you 0.5 itself. Because P1 cancels out, and here you get 10 into negative 0.3, because log of 0.5, okay, is negative 0.3. You do that in your calculator. Get your calculator open there. I think this is 0.5 log negative 0.3. Okay, remember the calculators in the computer, they use the base 10. I think they're saying Or any other way we can solve this? Even 10 log 10. Using the calculator, we can do that. And any other way we can do it? Mathematicians. Hmm? Hmm? Right. So I think that's the probably the most basic way. So it says there the answer being negative 3 dB. Okay. Now it says a loss of 3 decibels, that is negative 3 B is equivalent to losing 1/3 of the power. Right? 1/3 or negative 3, or rather 3 is just a 1/3. Okay, of the complete one. So remember, whenever you see a negative, when you get your answer as a negative value, that means there is a loss. Okay, there is a loss of power. But if you get a positive answer, okay, for example, maybe 1 dB or 2 dB, that means there is a gain in power. Another example here, or rather just continuing with that, it says that signal travels through an amplifier, right? And its power is increased 10 times. This means that P2 is equal to 10 of P1. So in this case, the amplification, that is gain of power, can be calculated as such, and that is 10 log 10 with the P2 over P1, and therefore P2 is same as 10 times the P1, and get your answer as 10 dB. So it's a positive value, therefore there is a gain in power. Okay. One reason that engineers use the decibel to measure the changes in the strength of a signal is that decibel numbers can be added or subtracted. So when we are measuring several points cascading instead of just two, okay, and I think the figure showing here, right, talking about this figure, says a signal travels from point 1 to point 4. In this case, the decibel value can be calculated as, okay. So if you look at this example here, from point 1, there is a loss of signal, right? Then till point 2, and then after that an amplifier is being used, and the signal increases, right, to 7 dB, and then again from point 3 to point 4 there is a loss of power. Okay? So to calculate the decibels, right, in this case it's negative 3 plus 7 minus 3, and the answer in this case is positive 1. That means from point 1 to point 4, okay, there is a gain of signal, okay, or gain of power, that is because of the value positive 1. Okay. Further, says sometimes the decibel is used to measure signal power in milliwatts, and in this case it is referred to as dBm, okay, in short as a subscript. N is calculated as dBm is equal to 10 log 10 PM, where PM is the power in millivolts. So it says calculate the power of signal with dBm of 30 or negative 30. Okay. So we can calculate the power in the signal as dBm, okay, because it's in milliwatts. 10 log 10 with the base 10 PM, that is milliwatts. Here the value of P is supposed to be calculated, right? For the power. Ten log 10 here. And can do is probably change this to basic export. Or simply back in here. Divide by 10 to get to that. Right. You can cancel, you're left with log base 10 m is equal to negative 3m. And then we can that 10 here. 10 to the power negative 3 is equal to u of m. And what is 10 to the power negative 3? Milliwatts, or that is same as 0.001 milliwatts. 10 to the power negative 3 is same as 1 over 1000. Okay, another example here. The loss in a cable is usually defined in decibels per kilometer. If the signal at the beginning of a cable with 0.3 or a negative 0.3 dB per kilometer has a power of 2 milliwatts, what is the power of the signal at 5 kilometers? So the loss in the cable, it says in decibels is 5 times 0.3, which is equal to negative 1.5 dB. We, in this case, it says we have to multiply by 5 because of 5 kilometers. Right? And the initial signal or the power is 2 milliwatts. You get the calculation. So dB 10 is equal to around dB, okay, decibels, equal to 10 log 10 with P2 over P1, which is equal to, that means the decibel value is already given to you, right? Which is negative 1.5. And therefore, using the base index form, okay, P2 over P1 is equal to 10 to the power, because 10 already being divided here. From the second line, okay. dividing by K, dividing by K. Let this work equal to negative 0.15 divided by K. So, and then taking two base form, K to the power 5, and this is equivalent to 0.1 right there. And then it says P2, okay, is equal to 0.71 P1, okay, and which is same as, because P1, the value, initial value, okay, is already 2 milliwatts. So that is why we multiply to 2 milliwatts. Right, so initial power was given there, which is in other words, we say 2 over P1 equal to 0.71, right? So in order to calculate, let's say P2, we multiply by P1, multiply by P1. P2 is equal to 0.71 times P1, and P1 is given as 2 times 1.4. That sentence already tells the signal at the beginning of a cable, right? With that many decibel in the power of 2 milliwatts. What is the power of the signal at 5 milliwatts? Okay. So that's an example of attenuation. Let's see if we have some additional examples or questions here. Okay, there is one question there, question 20 itself. Okay? This one. I want you to do this one in your exercise book. Using the formula here. So there are various types of questions that do come in exams. First one is just to calculate the attenuation. The second example, the second one is asked to calculate the power at source when the attenuation is already given. Or the third way to calculate the power at the destination when that is given. So the together, let's say, to say the attenuation of a signal is negative 10 dB. That means the attenuation is already given, negative 10 dB. So what is the final signal power if it was originally 5? So P1 is 5 watts. That's 5. So we divide this by 10, divide this by 10, so let's say P1 is equal to log the base 10. And remember P2 over P5 is just treated as 1 unit. Yeah. So base index, so we say 10 to the power negative 1 is equal to 2 over 5. And add this side, we get P2 equal to so that means the what is the final power? Final power is 0.5 volts. Right? So remember the negative decimal, then you should always keep in mind that if there is a negative decimal, there is a loss of power. So in this case, you should get something below 5. If your answer is more than 5, that means you should be concerned why it is more than 5 when there is a loss in power. Right? Okay, some past year types of questions here. So this is trimester 3, 2017. These two questions here. Okay, so we are already like talking on that, the 3 types of transmission impairment. So don't worry about question 5. Let's do question 6. All right, so this is quite simple here. That 10 log P2, which is 90, and 1. Okay. What answer do you get? That's 10 log 0.9 in a calculator, and you get 90. 0.046. Remember, it should be in decimal time because you are calculating the articulation. 0.4 without curve, you deposit it like that. Okay, that was one question from 2017 paper. Okay, this one, this is from 2019. You get that answer? 3000 words? Anyone confused here? The other questions are very similar here. Okay. So these types of questions will come in exams. Eh? Three ways. Eh? One is to just calculate the decimals. The other one is to calculate probably the power at source, and the other one power at the destination. Eh? All right. The second type, shall we continue? Yes. Right. The second type of cause or the impairment is distortion. Right? Distortion means that the signal changes its form or shape, and distortion can occur in a composite signal made of different frequencies. So, given an example, at the sender, okay, composite signals means many signals with different frequencies, right? So, if you look at the example there, and the same being received at the receiver's end, eh? And how the signal changes. Right? Now, the calculation of distortion is beyond the scope of this lecture here. Okay, so there is not much done, but just note that there are certain causes of distortion. For example, EMI, electromagnetic interference. Okay, if you have uh, heavy motors running in your vicinity, in your building, right? Heavy machineries, they can cause distortion. And if you have microwave ovens, right, they can cause distortion. If you have these fluorescent light bulbs, these lights, okay, they can cause distortion, right? And if you are putting the wires, the electrical wires together with the networking cables, they can cause distortion, right? So there are several things, right? Even the RFI radio frequencies, right? The TV antennas, right? All these types of hardware or devices can cause distortion in signals. Okay, so just keep in mind what distortion is, right? And how uh, it changes, right, the signal. The third type, okay, the third type of the cause, right, of the transmission impairment is the noise. And several types of noise, such as thermal noise, induced noise, crosstalk, and impulse noise may corrupt the signal. So there are several types of noise. I think probably in the next lecture is going to talk more about that. Just see the diagram, how it takes place here. Again, similar to distortion, right? The noise happens, the noise is introduced into the channel due to the use of heavy motors and other frequencies that are that affect the transmission. Just for your further clarification on that. So we have been using this material for CSC626. Those who have done it probably would remember. Here we have talked about a couple of things yesterday. CSC626 class. Talking about noise. Noise says can degrade or distort a signal on a network is measured in dB. EMI, right, caused by motors, power lines, televisions, copiers, fluorescent lights, microwave ovens, manufacturing machinery, and other sources of electrical activity, including a severe thunderstorm, right, can introduce EMI, okay, and that can cause actually noise. And one type of EMI is RFI, or electromagnetic interference caused by radio waves, and strong broadcast signals from radio or TV antennas can also generate RFI. So that is what I just stated. Now, example of what is basically noise here, sorry, crosstalk. Crosstalk is one of the types of noise indicated in your notes here. Okay. So crosstalk says occurs when a signal traveling on one wire or cable infringes on the signal traveling over an adjacent wire or cable. Look at this diagram here, right? So the wire which is actually transmitting the signal is this particular wire, but its signal is kind of affecting the other wires. So that is an example of what a crosstalk is. So it says the resulting noise of crosstalk is equal to a portion of the second line's signal. So it is, of course, the second line also will probably transfer some data. So with the introduction of noise from one of the lines affecting the other one, then the data can get corrupted. Okay. And of course, there are several types of crosstalk, alien crosstalk, near crosstalk, and far. Okay, not to worry more about that here, but just to know what actually crosstalk is. Noise can also be calculated, right? And in the next slide, it shows us how we can calculate the noise. And the noise is calculated, or the noise or signal to noise ratio is calculated actually. And the formula is, we say signal to noise ratio, that is SNR is equal to average signal power divided by average noise power. Okay. So SNR is actually the ratio of what is wanted, that is the signal, to what is not wanted, which is the noise. And SNR is the ratio of two powers. It is often described in decibel units. So average signal power divided by average noise power. That is how we calculate SNR. Given an example here, says the power of a signal is 10 milliwatts and the power of the noise is 1 microwatt. What are the values of SNR and SNR dB? Okay, so SNR is just calculated as a normal whole number or a value, right? Can be just a real number like 10,000 for instance. But SNR dB, okay, can also be calculated using another set of formula. Okay. So the two formulas are given here. So SNR is basically the average signal power divided by average noise power. So let's just do SNR in this case. So 10 milliwatts and the noise is 1 microwatt. So here you have to convert both into the same unit, right? 10 milliwatt and 1 microwatt. Which one is bigger, milli or micro? Milli is bigger. So, okay. And the other one is micro, right? So 1 micro is how many milliwatts? Or let's convert the milli to micro, eh? So 10 milliwatts converted to micro will be what? 10,000 microwatts? Milli to micro? I think it's multiply by 1,000. And here this way will be a divide by 1,000. So if you convert 10 milliwatts to microwatts, that will be a multiply by 1,000. So that's 10,000 and divided by just 1 in this case, which is equal to 10,000. I think this should be microwatts, not 1 microwatt. So 10,000 microwatt divided by 1 microwatt, of course, 10,000. So the signal to noise ratio is 10,000 in this case. Okay. And the same can be converted in decibels. Right? And the formula given there is signal to noise ratio in dB. So 10 log 10 and then SNR. Right? Just keep that in mind. SNR itself is average signal power of SNR E 10 load 10 SNR. That means the answer from that comes here. That will be ready. So in this case, 10 log 10 and you can simply calculate using your calculator. So 10 times log of Okay, just to look at the other types of or rather the definitions of impulse, noise, and all those here. Noise. Okay. A thermal noise, it says, is the random motion of electrons in a wire which creates an extra signal not originally sent by the transmitter. Right? So that is thermal noise. Induced noise says comes from sources such as motors and appliances. That is induced noise. And it says these devices act as a sending antenna and the transmission medium acts as a receiving antenna. That's explaining the induced noise. And then we have crosstalk. With crosstalk, we have seen the effect of one wire on the other. And the impulse noise, okay, is a spike. It says a signal with high energy in a very short time that comes from power lines, lightning, and so on. Okay. So the 4 types of noise mentioned in your slide here. Okay, the second example here, the values of SNR and SNR dB for a noiseless channel. Okay. Now, noiseless channel, this is something which we cannot ever achieve. Okay. There will be always noise in the channel. Okay. So this is like a theoretical assumption that that a noiseless channel may exist, okay? But in reality, it does not. Okay? So if you have a noiseless channel, that means there is no noise at all. That means your average noise is 0. Okay. So if you have a situation like that, okay, then your SNR will be an infinite value, right? And likewise your SNR dB will be infinite. So it says we can never achieve this ratio in real life. It is an ideal, right? It's just a theoretical assumption, but not possible. Okay. Two cases of SNR. The one with the large SNR and the one with the small SNR. So if you are getting a large SNR, that means your noise is small. Just looking at the formula here. For example, your average signal power is 100 watts. Let's say. Now, if you are having a large SNR, that means, let's say we're talking about 50 here, and we calculate X in this way. we're saying that large SNR 50 and we calculate X here. So in this case, what will be the value of X? X will be 2, right? So that means the noise is small, right? That's the noise 2, which is small. Right? If you are looking at a large SNR, noise is small. Now the other variation is you have a small SNR, for example, 20. If you have a small SNR, then your noise is big. That's what it says. Noise is more when you have a small SNR compared to when you have a large SNR. Noise is. So remember, don't think that large SNR really means lots of noise. Large SNR really means less noise. Okay, we'll take a 5-minute break here, and then we will continue with the next subtopic. Okay? Data rate limit says a very important consideration in data communication is how fast we can send data in bits per second over a channel. And data rate depends on 3 factors: the bandwidth available, the level of signals we use, and the quality of the channel, that is the level of noise that is present. Okay. Normally in copper cables, copper coaxial cables, there is more noise compared to fiber optic cables. Fiber has got less, or in some cases, very, very little noise presence in there. So the first one in this case here is talking about the noiseless channel, right? As I said, okay, in practical, this situation does not exist, right? You will always have noise in a channel. Okay? But here, noiseless channel, it was defined by this fellow Nyquist. Okay, so that's how the name came in, Nyquist bit rate. So it says for a noiseless channel, the Nyquist bit rate formula defines the theoretical maximum bit rate. Okay, as I said, theoretical, only in theory, okay, not in practical sense. Okay? Increasing the levels of a signal may reduce the reliability of the system. Right? So if you can remember, in our last lecture, we talked about the number of signals that can be sent in a digital signal. Okay, the digital signal. So that's what it says. Increasing the levels may reduce the reliability of the system. Consider a noiseless channel with a bandwidth of 300 Hz. Okay. Now remember, there are 2 ways to calculate bandwidth, right? Or we can say 2, not 2 ways, but 2 different measures. Right? Like one is in Hertz, the other was in BPS. If you can recall, I told you. Okay? Bandwidth can be calculated in 2 ways. One in using Hertz. Hertz is when you are talking about signals, right? And BPS when you're talking about bits per second, right? So signals, then it will be in Hertz. If it is bits or is it digital signals or digital data rather, then it in bits per second. So bandwidth of 300 Hertz, sorry, 3000 Hertz, transmitting a signal with 2 signal levels. The maximum bit rate can be calculated as. So the formula, okay, from the textbook. And this is the formula for calculating the Nyquist bit rate. Okay, so just note it. Nyquist bit rate. And Nyquist is talking about noiseless step. No noise in that. There's another program. Nyquist. 2 times bandwidth times 10 low with a base 2 and L indicates the level of the number of signal levels. Not 10, it's log to the base 2. Now the example that we are discussing at the moment here. So 2 times 3000. Okay. 3000 is the bandwidth and only 2 signals. So with the log base 2 of 2, which is equal to 6000 bps. And how it is done? Times 3000 times 2 with 2 signal levels. Right? So this is 2 times 3 is of course 6000 times 4. In your calculator, what you can do is simply what was it? You can just look. So log 2 divided by log 3. Because your calculators are log with the base 10. Eh? So say log 2 divided by log 2. That gives you 1. That's correct. 6000 times 1. And here, because we are calculating bit rate, okay? Though the bandwidth is given in hertz, right? But the answer is BPS. So there, as I said, 2 ways to do it. So bandwidth, remember bandwidth can be also in BPS, right? But here, so because the question is to calculate the bit rate, the bit rate in this case we will need to BPS, right? Just clarify this one. I think we started with this one. There was one Somewhere else we did this. Now last week's lecture. I think it's actually in your calculator because it's not page 2, it's page 10. Eh? So that you recall where else we used this? We used it in our last week's lecture as well. Those mathematics students used to tell me last year. Or just log to divide by log. Log of 0. Okay. Oh yeah, we did another exam. That's what I said. Because okay, okay. So whatever number is on the top, use that number, divide the log. Right? So in case if this was log, if it was log 10, then we just say log 10 divided by log. Okay. This number, and then you have. Let's look at the next example. Next example will give you a fair idea of how. This one is again on a noiseless channel. So whenever it's talking about noiseless channel, we need to think of Nyquist bit rate. Transmitting a signal with 4 signal levels. For each level, we need to send 2 bits. The maximum bit rate can be calculated as again, same formula. 2 times 3000 times log with the base 2 and 4 signals. So 6000 times log. And in your calculator, because it's base 10, so I'm writing base 10, divide by that. Divide by log of 2. Like that, eh? And this will give you log 2, right? So 6000 times log 1000. All right, the next example here says we need to send 265 kbps over our noiseless channel with a bandwidth of 20 kilohertz. How many signal levels do we need? Okay, so basically here it is asking you to calculate the value of L given the amount of data that can be sent, or the bit rate. The bit rate is given 265 kbps. Now remember 265 kbps, K basically indicates the kilo, right? So we will say 265,000 bps. So the answer to bps here is equal to 2 times 20 kilohertz, that is same as 20,000 hertz. Okay. Times the hertz and beats per second are similar, same. Times log raised to n L, right? So times 20, 40,000 L right back 40, 6.65. L. And here we can change it to base index form. Yeah. And let's go to the power 6.5. Now, one thing to note here, if you can recall, in our previous lecture, we talked about levels there as well. And we said the levels can only be a base of 2, with a base of 2 or a power of 2, 4, 6, 8, like that. The levels. Do you get that 98.7 levels? Right? 2 to the power 6.625. Changing that into base index form. Right? L is equal to 2 to the power 6.625. Now in this case, remember the answer that you get is 98.7 levels. However, I say since this result is not a power of 2, okay, if that's what I said, if you can recall from our last lecture, remember that we also calculated L, the value of L in digital signals. L has to be always a power of 2, I mean the base. Okay, so 2 to the power 2, 2 to the power 3, 4, 5, 6, like that. So it says we need to either increase the number of levels or reduce the bit rate. So 98.7, okay. So what I am saying here is you get 2 to the power 2 or 2 to the power 3, 4, 2 to the power 5, 2 to the power 6. What is 2 to the power 6? 64, right? Yes. And what is 2 to the power 7? 128. So 98.7 lies between these two values here. But then it says if we have 128 bit, 128 levels, the bit rate is, so with exactly 128 levels, if L was 128 levels, then the answer should be 280 kilobits per second. If we have 64 levels, in case we go down and use 4 levels, then the answer will be 240. So here, 98.7 levels is not an acceptable answer. The acceptable answer is only either 64, 100. Okay. So, if a question like this comes, then you have to explain your answer, showing that if in case we use something which is lower than that, which is 2 to the power 6, the 64 level, then the answer will be so and so. So what you will do, you will basically place 64 in place of L and calculate the answer. And likewise place 128 in place of L and showing the difference. Okay, so that was on noiseless channel. But I did not find any question on the noiseless channel at the moment. So all are on noisy channels. Okay. Much. Right. The next subtopic that we shall. When does our class finish? 11. Okay. I think we will stop here then. So we will start from slide number 22 in our next class. Okay. There's lots of calculations, right? In this rather in this lecture. So we'll stop here for today. So whatever we have done, please, I suggest you to go back and just relook at it again. Just try the examples again, right? And similar types of questions will come in your exam.